thanks a lot for coming to this session. I know it's a long conference and you're probably tired of taking in information. There will be some science in this talk, but so try and stay awake. Hope you've had enough coffee. So Phasecraft is the quantum algorithms company. We're working on trying to get quantum algorithms to be efficient enough and optimized enough to actually run on hardware that exists or now or in the near future. And we're founded by myself, Ashley Montanaro, John Morton, who are all have all been working in the field in quantum information and quantum computation for over 20 years, and we're based out of Bristol and London. So if you look at quantum algorithms, what you want is really to have an intersection of three different things. We want algorithms that are commercially useful. We would like to be able to run them near term, and of course, quantum algorithms need to beat classical algorithms or they're not competitive. And if you just put the known quantum algorithms in this Venn diagram, you find various things fiddle over here. And of course, the million or maybe even billion-dollar question is what's in the intersection of all these three. At Phasecraft, one of the things we believe that is we want to pull into that intersection of being commercially useful, outperform classical algorithms, but actually be runnable on near term is simulating quantum many-body systems. And we believe that's one of the most promising early applications of quantum computing, and we're not the only ones to think that, but we're doing perhaps more than others in trying to bring that physics simulation into that point of being usable and actually runnable. So if you look at quantum hardware development over the last decades, it's been steadily improving. Even if you plot, and this is plots from real data taken off either real hardware or the scientific literature, not roadmaps and PR exercises. But if you look at what you need in order to run that didn't work. If you want to look at what you need to actually run a real-world application, for example, simulating a material like, I've taken the example of strontium vanadate here, which is a material of interest to battery technologies, there's a huge gap between what the hardware is able to do even now and what you would need in order to actually simulate that material and model that material on a quantum computer. So over the years since we founded Phasecraft, we have been working on bringing down this top line and of figuring out ways to do this much, much more efficiently than anyone else is able to do. And so if you look at the progress over the last years, the hardware has steadily improved, but the algorithms that Phasecraft has been able to produce have made huge gains in terms of efficiency, bringing much closer the point where we're actually able to put these on real hardware. So and if you extrapolate this out, we actually believe that we may not be that far away in that many years, and this is probably a controversial statement in the current atmosphere in the quantum computing industry, but we actually think that it isn't so many years, it may be 2 to 3 years out, before the first relevant applications start to be within reach of hardware. Now, humans are really bad at understanding multiple exponential scales and multiple orders of magnitude. So I want to give you a sense of what we've achieved in terms of the improvements in algorithm design in Phasecraft. So if we take the best previous algorithm for simulating and modeling this particular real-world material, this is where the circuit depth you would have needed to run a step of this algorithm. And let's look at the difference between that and where we are today in Phasecraft with our proprietary techniques. So that previous circuit depth is just way beyond what could be done on near-term quantum computers. You clearly needed a scalable, fault-tolerant quantum computer. But it turns out that if you're clever and put a bunch of very smart people on thinking very hard about how to solve that real problem on real hardware, and not just with generic textbook techniques, but invent new maths and new techniques to bring down the complexity, I can talk for quite a long time until we get to where we are now and what the resources we would need to actually model that material on hardware. That's how big an exponential 6 orders of magnitude improvement looks like when you actually just zoom through it. So we've not just done this for one material. In Phasecraft, we have a software pipeline that we can take a description of a material, and we can also apply this to molecules, and it goes through a whole bunch of stages that have algorithmically coded up the proprietary methods we developed to actually design more efficient algorithms for these types of problems. And out the other end, put a description of material on one end, and out the other end comes a quantum circuit that is ready to be run on a quantum computer. The hardware to run this is not quite there yet. Circuit depth 880 is not quite within reach of current hardware, but it's a lot closer than the 6 orders of magnitude more you would have needed before our work. So at this point, I like to quote something that was in a report to the US Congress on classical computing, actually, not about quantum. It was a nice quote that said that theory beats Moore's law by multiple orders of magnitude. Even with exponential year-on-year improvement in quantum hardware, the types of algorithmic improvements we're able to make, even if you believe that hardware will continue to double in capacity every year in quantum, which is, may or may not be true, we've knocked, with this work, 10 years off when you would first be able to run real applications on quantum hardware. So at that point, I would like to hand over to our principal scientist, Glenn Jones, to actually give you some information in a brief period of time of what's behind these results and how we actually achieved these for these applications. So Glenn, take it away.
Right. Hello. So let's just get used to this. Yeah, so if we think about trying to simulate materials, if we just look at a simple toy model, which is probably the simplest model you can come up with that contains some of the complex correlations in real materials, this is a system that for over 50 years is still unsolvable. If you want to solve this exactly on a classical device, even for 17 electrons, it took a 512-node supercomputer in 2005 to achieve this. And this is just for a toy system, let alone a real material system. If we jump ahead to sort of more recent work, and we've seen this in other presentations, there's the Google quantum supremacy experiment. That was done on 53 qubits and with 20 time steps. But if we look at what Microsoft sort of estimated to simulate nitrogen fixation in the nitrogenase COMO enzyme, that requires more than 10 to the 9 qubits and more than 10 to the 15 time steps. So as Toby was saying, this sort of sets the scene and the challenge that there is and the gap that we've got of how do we bring down the complexity of simulating a real material, a real chemistry, onto something that we can do on near-term devices. So the work that I'm going to show you was done through the auspices of an Innovate UK project, which is a scheme that's run in the UK to support, say, feasibility studies between startups, between end users, and academia. And at the time we did this project, I was working with Johnson Matthey, who are a UK sustainable technologies company, and they focus on doing things like clean air in your exhaust pipes, traditional catalyst technologies, fuel cells, electrolyzers, and have got nearly just over 200 years experience working with platinum group metal chemistry. And just for the sort of business context of where this fits in an organization like Johnson Matthey, you can find simulation across the whole sort of product life cycle, whether you're looking at engineering in the business or statistical approaches. But we're working with the materials and chemicals research group that was sitting in the product development, where they use classical methods to try and simulate the materials and chemistry. So within batteries, what are some of the key challenges? So over on this side, we've got just a very simple schematic of what a battery material or a battery looks like. You've got your cathode, your anode, and we have some separator, which could be solid state or could be liquid, depending on your technology. And then you have some charge carrier, in this case, the lithium ions. So if we just focus on the cathode, the challenge here is that we can have many different chemistries, so lithium iron phosphate, nickel manganese, cobalt, and so on. But none of them are optimal. So some have very high energy and power, but low safety. Some have very high charging rate, but not very good power. And so there's still, in order to make electric vehicles and other sort of technologies useful, there's a lot of optimization that can be done here. So if we zoom in a little bit more into battery materials specifically, we can think at the length scale of how does a battery work in the vehicle, how are we going to simulate and put the cell design together. But then once we've got the cell, what the clever bit is the material that goes inside there. So we could be interested at the microscale of the transport of the lithium, the stability of the nanoparticles in there, which are governed, for example, by elastic properties, which you obtain from the atomic scale. Or you could be interested, for example, in a voltage curve. And this is given by the electrons and atoms moving around at the quantum scale. But the problem we've got to do quantum simulation accurately, we have our sort of standard approaches, density functional theory, a pragmatic balance between cost and accuracy. But for complex battery materials, these actually quite often fail, particularly for the complex oxides we've got. There are approaches like full configuration interaction, which is fine if you've got 25 electrons, but we're interested in hundreds and thousands. So this is the challenge that companies like Johnson Matthey are hoping that people like Phasecraft can solve with quantum computers. So how does Phasecraft do this? So just sort of elaborating on the workflow that Toby took you through, you can start off with your crystal structure. So in this case, it's strontium vanadate. We can obtain the electronic structure of this and pull out what the orbitals or our quantum states are. But if we just use this as it comes straight out of a DFT code, it's not useful. So we then want to try and represent this as compactly as possible. So we move to something called the Vanier basis, which sort of spatially localizes our orbitals as tightly as possible. And what this does is it helps us when we move to the next step for the fermionic encoding, is that we end up with a Hamiltonian that has sort of regions that are either very densely populated or very sparsely populated, and you can split this up into regions where we can use Phasecraft's hybrid fermionic encoding to actually begin to get this system down into the quantum device. The next step after that is how do we turn our fermionic encoding into a quantum circuit, and this uses a variety of algorithms and heuristics, but essentially we end up with the full workflow in Phasecraft's tool that we can take any number of materials, put them through this, and it will deliver us an optimized circuit at the end. So if you're interested in the technical details, there's a paper that's just been accepted in Nature Communications and is available on arXiv if you want to read more. So once we've done that, we can, actually as part of this project, we delivered a materials modeling database. So you can also go online to look at this. You can click on the database. You can come up with your application area of interest. So for example, we're interested in batteries. It'll pull up the different materials that we've studied for batteries, and you can go through what was the naive baseline of the resource estimates, and then you can see what the Phasecraft algorithms have done in reducing the depth requirements of the circuits. And then there's also a whole sort of information sheet on the approaches that we use, the different parameters that are involved in there. So I'll skip through that. And basically what we've seen, just to summarize and kind of emphasize the kind of improvements that we see. So for strontium vanadate, that was a 10 to the 6 improvement. But it's not just for batteries, it's for semiconductors, solar cells, superconductors. All of these we saw significant improvements over the state of the art. And to sort of finish where Toby handed it over to me, this has taken Phasecraft from this point where there was this wide gap to where we are today, that we really do believe that useful materials modeling is in touching distance of being achievable. And thank you.
Thank you very much. Are there any questions? We have a few minutes to take questions. Yeah, I'll bring the microphone to you.
Yeah, hi. I was wondering, one of the problems the industry currently also faces, other than finding better chemistries, is scaling to large volumes. And I was wondering if you can help with that problem also. So once you have maybe a better chemistry, if you can also extrapolate when this goes to, let's say, millions of vehicles.
I'll leave that one for you.
Yes, so there are certainly ways that we're looking at this with sort of quantum enhanced classical methods. But I don't know how much we can say that at the moment, but basically where we can use the quantum device. And it's a bit like multi-scale strategies that you see in the classical world, that we can start with ultra-accurate numbers, which we can try to get from our quantum device, and then feed these into a classical workflow that can help us leverage some of the challenges or some of the experience to tackle the challenges that we've learned in the classical materials workflow.